Welcome to our quantum deep dive. Imagine a world where your communication is truly unhackable. Or maybe a computer solves problems in, seconds that would take our best machines millennia. Well, that's not really science fiction anymore. Today we're diving into quantum information theory. It's this fascinating field making those maybe impossibilities a reality by fundamentally rethinking how information works.
Indeed. And for this deep dive, we've really dug into Jörg Goschneppe's illuminating essay, Quanteninformationstheorie, Grundlagen and Anwendungen.
Mm-hmm.
Our mission, really, is to distill the most impactful nuggets from it, helping you grasp how quantum mechanics is fundamentally revolutionizing how we process, transmit, and importantly, secure information. It's about moving from the theoretical to the truly transformative.
And the why here is crucial, isn't it? This isn't just abstract physics floating out there. This field is opening up entirely new technological possibilities, things that will redefine secure communication, computational power, maybe even our understanding of reality itself. It directly impacts the digital world we live in and, the one we're building. So, okay, let's try to unpack this a bit. We're all pretty familiar with classical information theory, right? Largely shaped by Claude Shannon's brilliant work. It's built on those binary states, the deterministic we's and ones, simple, elegant, foundational stuff. But quantum information theory, it takes this huge leap beyond that. How does it fundamentally redefine what information even is?
Well, what's truly fascinating here, I think, is the introduction of the qubit. See, unlike a classical bit, which is definitively either 0 or 1 at any given moment, a qubit has this remarkable ability to exist in a superposition of both states simultaneously. Think of it not as an either switch, maybe, but more like a blend, a spectrum of probabilities until you actually measure it. Mathematically, you'd write a general state of a qubit as a linear combination, qubit high plus way I. Now, I and Kia, they're complex coefficients, and they aren't just abstract numbers. They're magnitudes squared, so I and 2 and echo tell you the probability of measuring a 0 or a 1 when you look. This means we're dealing with amplitudes, not just simple probabilities, and that allows qubits to show wave-like interference patterns. And that unique property, that interference, is what directly fuels the power of quantum algorithms.
So wait, a qubit can actually be both 0 and 1 at the same time. That's quite a conceptual leap. It sounds almost inherently fuzzy.
Absolutely. Precisely. And this ability to be in multiple states simultaneously is what really unlocks the revolutionary power. Then you combine superposition with other quantum phenomena like entanglement.
Yes, entanglement.
Right, where qubits become intrinsically linked, meaning the state of one instantly influences the other, no matter how far apart they are. And quantum parallelism, which lets a single quantum computer explore many different computational paths at once. Well, you gain capabilities that are just unattainable for classical computers. It's these properties that let quantum computers solve certain problems with, frankly, astonishing efficiency.
Okay, this raises an important question then. If the nature of the bit changes so profoundly from bit to qubit, what's the fundamental difference in how we actually quantify information in these two worlds, the classical versus the quantum? It can't just be a different formula, can it? It seems deeper.
You're right. It is a deep conceptual shift. While Shannon's classical entropy, Hx equals or multiply log 2 pi, measures the average uncertainty or information content in classical signals, it reflects a definite, maybe unknown state. The quantum world uses the von Neumann entropy, defined as SPAR, that's Rho, represents the density matrix of a quantum state. So the shift isn't just about a new equation. It reflects that information in the quantum realm isn't about distinct on or off values. It's about probabilities and that inherent fuzziness of a system in superposition. It quantifies information that's, inherently intertwined, and you can't always pin it down to a single classical value without, disturbing the whole system.
So we talked about what a qubit is, how we measure its information, but how did we even get to these kind of mind-bending ideas in the first place? To really get the power and the paradoxes of quantum information, we probably need to look back a bit, right? At the origins of quantum mechanics itself, where these strange rules first popped up.
Exactly. The whole concept of quantum information really grew directly out of those revolutionary breakthroughs in early 20th century quantum mechanics. You had pioneers like Max Planck back in 1900 introducing the idea that energy isn't continuous but comes in discrete packets, or quanta, E equal I's. Then 1905, Albert Einstein's work on the photoelectric effect showed that light, which everyone thought was a wave, also behaves like particles. These weren't just like physics milestones. They led to this stunning realization that reality at its smallest scale is fundamentally probabilistic and, discontinuous. And Niels Bohr's atomic model in 1913 further cemented that idea of discrete energy levels for electrons.
And then came the big theoretical frameworks and some really bizarre thought experiments too, didn't they? I'm thinking of that famous cat in the box.
Precisely. The formal mathematical frameworks really took shape between 1925 and 1926. Werner Heisenberg developed matrix mechanics, and Erwin Schrödinger introduced his famous wave equation. IC, AR, that's still the fundamental equation of quantum mechanics today. And yes, of course, Schrödinger's cat thought experiment from 1935. It just vividly illustrates the paradoxes of superposition and the crucial role of measurement in quantum systems. It highlights how a system can exist in this indeterminate state cat, alive and dead until it's observed, really challenging our everyday intuition.
But theory is one thing. What about the experiments, the ones that actually proved these strange ideas were real, moving them from philosophical head-scratchers to actual verifiable science?
Crucially, yes, experimental evidence backed up these concepts. That provided the bedrock for quantum information. The double-slit experiment is the famous one. It demonstrates wave-particle duality beautifully. An electron acts like a wave if you don't watch it, creating an interference pattern. But it collapses to behaving like a particle if you do watch it.
Just looking changes it.
Right. It hammered home the critical and irreversible role of quantum measurement. The act of observing fundamentally changes the system's state. And maybe even more profoundly, John Bell's inequalities, formulated mathematically in 1964, set these theoretical limits on correlations you could expect in classical systems. Then experiments by Elaine Aspect in the 1980s confirmed that quantum systems violate these inequalities.
They break the classical rules.
Exactly. Proving definitively that entangled particles are profoundly connected beyond any classical explanation. That's Einstein's spooky action at a distance. It's real.
So what does this all boil down to for those core principles, the ones that really underpin quantum information and give it its unique power?
It means superposition is real. It's a genuine phenomenon. A quantum system can exist in multiple states simultaneously, and that's a direct consequence of its wave-like nature. Then there's quantum coherence. That's the system's ability to maintain these delicate superposition states, and importantly, their phase relationships over time. This is where quantum computing gets its potential power. However, interactions with the environment, even tiny ones, quickly lead to decoherence.
The breakdown.
Yes. The system loses its quantum properties and collapses into a classical definite state. It's like trying to balance a pencil on its tip in a shaky room, the slightest vibration, and it falls. That's decoherence for a qubit. Very sensitive. And finally, entanglement, where two or more particles become intrinsically linked. Measuring one instantly affects the other no matter the distance. It's the most counterintuitive, perhaps, but also an immensely powerful principle.
Okay, so this is where these really mind-bending principles start to transition from pure theory to actual tangible impact. How do these unique quantum properties actually lead to new kinds of algorithms? Algorithms that can solve problems classical computers just can't handle, or at least not efficiently.
Right. Quantum algorithms leverage superposition and entanglement to tackle problems with far greater efficiency than classical ones can manage. Perhaps the most famous example is Shor's algorithm. It can efficiently factor large numbers into their prime components. And this presents a direct, maybe even existential threat to many classical cryptographic methods, like RSA, which rely entirely on the fact that factoring very large numbers is incredibly hard for regular computers.
So basically all our digital locks today, the ones protecting our banking, our communications, even national security, they could become as easy to break as a simple padlock. That's a pretty sobering thought. What might take a conventional supercomputer thousands, maybe millions of years, a quantum computer could potentially do in minutes or hours.
Potentially, yes. And that's exactly why it's so disruptive. Shor's algorithm pulls this off, this exponential speedup, by cleverly finding periodicities using something called the quantum Fourier transformation. It's just vastly more efficient than classical methods for that specific task. And another incredibly important one is Grover's algorithm.
Grover's, right. What does that one do?
This one provides a quadratic speedup for searching unsorted databases. Now, quadratic isn't as dramatic as exponential, but it's still significant. To put it in perspective, imagine a classical search needing, say, n operations, in the worst case, to find something. Grover's algorithm can potentially find it in roughly the square root of n steps.
So for a database with 1 million entries, instead of maybe 1 million steps, Grover's might do it in about 1,000.
Roughly, yes. It's a major improvement for searching really large data sets, or just brute forcing it is totally impractical.
That sounds incredibly powerful. But, okay, there's always a but with something this revolutionary, right? What's the catch? It sounds almost too good to be true. What are the big limitations right now?
You've hit on the core issue, and this raises a really important question. The biggest hurdle for practical quantum computing right now is precisely that decoherence we mentioned earlier.
The fragility.
Exactly. Qubits are incredibly fragile. They lose their quantum coherence, their quantumness, very quickly due to environmental noise, tiny temperature fluctuations, stray electromagnetic fields, even things like cosmic rays. And this fragility leads directly to errors in quantum computations, making them unreliable if you don't handle it.
So you need error correction, presumably.
Absolutely vital. Quantum error correction, or QEC, is a huge field of research. It involves developing these elaborate codes. Think of the Shor code, which uses 9 physical qubits to protect 1 logical qubit, or the Steen code, using 7 physical qubits for 1 logical one, all designed to detect and correct these errors. But here's the extra challenge, the no-cloning theorem. It's a fundamental principle that says you cannot perfectly copy an unknown quantum state.
So you can't just make backups like we do with classical data.
Exactly. You can't simply duplicate qubits for redundancy. So that standard approach to error correction, just making copies, is off the table. You need much more clever schemes.
So, okay, given these profound challenges, how is all this theoretical and algorithmic power actually translating into real-world applications right now, or maybe in the very near future? What can we realistically expect to see?
Well, one of the most mature applications actually is quantum cryptography, specifically quantum key distribution, or QKD. The most well-known protocol here is probably BB84, developed by Charles Bennett and Gilles Broussard way back. The core idea is really ingenious. Alice sends qubits to Bob, but she randomly encodes them in one of 2 different quantum bases. Bob then measures them, also randomly choosing which bases to use for each measurement. Now, if an eavesdropper, let's call her Eve, tries to intercept and measure those qubits to figure out the key.
She disturbs them.
Precisely. She fundamentally changes their quantum state, unavoidably. Alice and Bob can then compare notes on a subset of their measurements and detect this interference because they'll see a high quantum bit error rate, or QBER. They'll know immediately the key has been compromised before they use it to send any sensitive information.
So it's essentially unhackable in the sense that any attempt to listen in leaves this physical, detectable trace. You can't just passively eavesdrop on quantum information.
That's a great way to put it. It's security based on the fundamental laws of physics, like the no-cloning theorem. It means you cannot undetectably intercept the key.
Right, the detection is key.
Exactly. Any attempt to eavesdrop introduces that disturbance. Alice and Bob detect it, discard the compromised key, and generate a new one. It doesn't physically prevent interception, but it guarantees detection, which ensures the ultimate security of the shared key. And beyond just encryption, quantum information theory is also opening up entirely new possibilities for quantum communication networks. This could eventually lead to what people are calling a quantum internet.
A quantum internet? What would that even look like? How would it be different from the internet we use every day? Would we be like sending qubits through fiber optics instead of classical bits?
In essence, yes. It would allow quantum information, particularly entangled states, to be distributed and maintained coherently over vast distances. Now, this isn't just about sending classical data faster. It's about enabling truly secure communication using QKD on a global scale. And it could also facilitate distributed quantum computations, where maybe different quantum computers could link up, share entanglement, and tackle even larger, more complex problems together. Experiments are already pushing this forward. People are demonstrating quantum teleportation transferring quantum states over really long distances. For instance, China has achieved this over more than 1,200 kilometers using satellites. That's a huge step towards realizing that quantum internet vision.
Okay, and what about the big one, actual quantum computers? We hear so much about Google, IBM, D-Wave. Where are we really with those massive machines that everyone's so excited about? How close are they to being, practically useful?
Yeah, that's the billion-dollar question, isn't it? So while classical computers process bits deterministically, one step after another, quantum computers leverage superposition for this inherent parallel computation and quantum interference to get those potential exponential speedups for specific kinds of problems. And the major players are definitely pushing hard. IBM Quantum, for example, they're continuously developing more powerful processors based on superconducting qubits. Google, with its Sycamore processor, famously demonstrated what they called quantum supremacy back in 2019. They performed a specific calculation in about 200 seconds that they estimated would have taken the world's most powerful classical supercomputer something like 10,000 years. And then you have companies like D-Wave focusing on quantum annealers, which are more specialized quantum computers designed for optimization problems. However, those challenges we talked about, severe decoherence, high error rates, and just the immense difficulty of scaling up to millions of stable, interconnected qubits, those remain really significant hurdles. The entire field is working incredibly hard to overcome them. It's fundamentally a race against quantum fragility, trying to build bigger and better systems before the quantum states fall apart. So, to kind of summarize, quantum information theory is truly revolutionizing cryptography, computing, and communication. It's quite a shift. We've really moved from these purely theoretical concepts like superposition and entanglement, which seemed almost philosophical at first, to actually designing algorithms that could potentially break modern encryption or dramatically speed up certain types of searches. It's a field built on the profound, sometimes bizarre strangeness of quantum mechanics, but it's turning those peculiarities into genuinely powerful computational tools.
And it seems like while quantum cryptography, the QKD stuff, is already finding some niche applications today, maybe for high security needs, the full potential of those general-purpose quantum computers and a truly global quantum internet is still very much in active development, still feels a bit down the road. So the coming decades will be absolutely crucial, won't they, to see how these groundbreaking technologies actually integrate into our lives and reshape our digital world, moving from, lab experiments to real everyday impact.
Absolutely. And this whole incredible journey, and when you think about it, from the very beginnings of quantum mechanics with figures like Planck and Einstein grappling with these new ideas, through the mind-bending paradoxes that Schrödinger highlighted, all the way to the cutting-edge work being done today on qubits, error correction, and these advanced quantum algorithms, it really underscores the transformative power of understanding information at its most fundamental quantum level. It's a real testament to human curiosity and ingenuity, constantly pushing the boundaries of what we thought was possible.
It really makes you wonder, doesn't it? How will quantum information ultimately reshape our understanding of reality itself? And maybe more practically, what new problems will you, our listeners, potentially be able to solve with these incredibly powerful tools once they're fully realized and accessible? Will it open up entirely new scientific frontiers we haven't even conceived of yet, or just fundamentally change how we interact with the digital world every day? Our deep dive today, pulling out these key ideas, was based on the insightful work of Yorgo Schneeppot in his essay. If you're interested in exploring this topic in more detail, you can find more information at schneeppot.de. That's SCHNEPPAT.DEE. Well, that's all the time we have for this deep dive. Thank you so much for joining us.